we're at the point last lecture which we were in the middle of having fun and games with the delta function. And we stopped at the point where we define one of the manifestations of the delta function. And we even showed that the integral over it between minus infinity and infinity is 1, using the contours in the complex space, which I'm not so sure all of you really grasp till then, but let's see. Yeah. Let me show another property of delta function, which is which the answer is F0, of course. Emphasize any integral with delta is a present. This is integral we'll ever see. Okay, but let's verify it for this definition of delta. Okay, so instead of delta, we'll put in the definition. Writing down the definition. Okay, let's do a change of variable. You remember I have x and dx, so epsilon is cancelled out. Sure.
We say that y is equals x over epsilon, right?
It's just
how do we know if epsilon is like negative or positive, and then the integral switches?
well, at the moment I didn't define. I just defined the transformation of variables. That's I'm always allowed. Doesn't matter if epsilon is plus or minus,
Right.
or whatever. Okay, so that's all I did at the moment. Okay. Now I take the limit, and it doesn't matter if epsilon is positive, negative, or what not. If it goes to 0, this is f of 0. Okay, f of 0 is outside And this we proved the previous lecture is 1. Okay, so I've shown that this definition contains an additional property of delta function. An integral over delta function times f is f of 0, the same behavior we have shown here. Okay, and we can continue and show it for all other properties, but at the moment, let's just take this definition as given. Okay, now I'll massage this definition a bit and rewrite it in a different way. So, just perform. This is an easy integral to perform. We'll give you e to the power x over epsilon minus e to the power I minus I x over epsilon divided by 2 is sine. Exactly what appears there. I'll add the limits. This identity from now on will be one of the most useful identities that you have ever encountered in physics. It will repeat itself in solid state physics, will repeat itself if you do field theory, anything. This is an extremely useful identity. And it's very easy to work with. You remember that we had this interval, we wrote it, which is delta of A minus B. Let me prove it using this identity. Okay, so instead of these guys, I'll write the definition of delta function. The first delta. I wrote the second delta. Now, and this step returns endlessly. I first perform the integral over dx. So I'll change the order of integration. Okay. So I'm moving integration over k and k prime. E to the power ika minus and e to the power ik prime times minus b doesn't depend on x, right? So I can write it here. I rearranged the multiplication of e to the power I, whatever appeared inside. Okay, but this up to 2 pi is a delta function, by definition. Borrow one of the 2 pi's for here for the definition of the delta function. Perform one of the integrations over, let's say, dk prime. It's minus because here it's k plus k prime. This is delta of a minus b. Which is the result we gave in the previous lecture. As you see, straightforward to prove.
Can I ask this?
Sure.
From the last line here to the first one up, if you multiply everything by minus a, why did you lose the minuses there?
I lost them because I was slow to put minuses everywhere. It doesn't.
Doesn't change it?
No.
Wait.
So here it will be plus and minus.
Oh, and it's symmetric. Okay. Okay, now.
But you're right that I was slow.
No, I just didn't understand something you didn't get at.
So anything, if you're in doubt about what occurs with some complicated expression of delta function, the easiest thing, go back, go back to this definition, the best definition to work. Okay. Just another comment. and using this formulation, what happens if I have a delta of vectors? In three-dimensional space, if I want to specify a point, it's not a scalar, it's a vector, so I should be able to use delta functions also. No problem, go back to the definition. Right? That's the natural extension of the definition here. And that I don't want now to write it as vectors. I want to write it down in x, y, and z. So I know how to write this guy. And I know how to perform a dot product. Sorry, one mistake. Because integral is over k. Okay, so what is the result? These are three delta functions multiplied by each other. Makes sense. In order to do for two vectors to be zero anywhere except at the position of the vector r0, you have to have the same x, the same y, same z. Enough that one of them is not the same, it should be zero.
Can you remind us how it works when you get the different coordinate system, like polar coordinate system?
We will run, if I would have used here a different coordinate system, let's say you don't like this system, you like polar. Okay? So, did you copy? Okay. No problem. Coordinate system is matrix. Doesn't contain the mathematics. So here k is just the absolute value of k. And here the Jacobian will be 4 pi, right?
Yeah.
If I'm-
It will affect the final result, like delta.
we'll do it. I think it's 4 pi. Okay. What is this in polar coordinates? Well, I have here a dot. How do I perform? Well, let's stop a minute and look what happens. If I have some direction of k and some direction of r minus r0, so what is the scalar multiplication of these two vectors? This the absolute value of this times this times theta. So, to make life simple, I decide to put theta in a specific direction. Let's say choose it in the direction of r minus r0. And I allow, why not? And I'm choosing the polar coordinate. I always choose some direction. I don't bother to write here between the absolute value of k because in polar coordinates it's always between 0 and infinity. Okay? This is more complicated than is needed, but it appears again and again in physics. Therefore, how do I do this? Looks terrible, right? No, actually it's not. No.
Yeah, of course, then.
That's you can change variables. So you get instead of sine theta, you get but it won't affect like there won't be any size factor or difference between the result here and delta that just is x, y, and z.
No. There shouldn't be, because it's not.
I know that that's logical that there won't be any difference because that's just another way to describe the same system practice.
The physics or deep mathematical structure can't change because I choose coordinates. That's all. So if you get a change, it's because you made a mistake.
Okay.
Okay, so what do you get here? Let's say choose mu is cosine theta. Okay, let's do it stage by stage. Okay, first integral on speed. 2 pi. Not in the grade. So and I want to use mu sign. I have cosine going between minus pi and pi. That will minus pi. Yeah.
Then you should like divide the function by.
Oh, I have to. You're completely correct. I have here divided by. Okay. And how do I continue here? No, first of all,
yeah, we can this.
No, but you don't get rid of it completely.
Yeah.
You have to be a bit careful. And you know what? That's the reason why we don't do it at this point. Again, you have to go into a contour. But believe me, you'll get your delta functions. Whoever wants to go in a bit deeper here, as I said, it's not in my material, but you can show that you'll get a delta function also on R minus R. Okay, I don't want to continue here and confuse you a bit more in deeper mathematics that we don't need at this point. But whatever the definition of delta, you can work with. The important thing is this is a very convenient definition, and you can work with it. Okay, so we'll stop here. Whoever is interested, I suggest check Boris or Arfin for the details, and we'll get the result. Okay. Why did we go into this whole game? we wanted to find the eigenfunctions and eigenvalues of X, operator X. Right, that was the reason that we did it. So, that was the equation that we started, the equation for eigenvalues and eigenfunctions of operator X. Okay. What's the first thing that we know about eigenvectors?
If they are
Orthogonal. Right. So, if I take another eigenvector, so necessarily this should be a delta function, right? Let's check. Oh, we did it a moment ago. Right? It's A and B. But this is not from the delta function.
it shouldn't be 0.
It should be 0 if x is not equal to 0. It should be 1 if x is equal to x0.
What is it?
No, it's not what it says. It tells you basically that it's 0 if x is not equal to x1 and ill-defined at the point that x1 is equal to x. The integral over it is 1. This is not 1. So, Dirac, when trying to define quantum mechanics in the language of linear algebra, was hit by this problem and came up with an elegant but problematic solution. You have two eigenvectors that are in a continuum. Follows the Dirac orthogonality. Not the usual orthogonality. Operatively, it's an elegant solution. Okay, if I'm dealing with an operator that has a continuum of eigenvalues, like the position, okay, don't worry. It will follow the Dirac orthogonality, not the usual orthogonality.
But you just can't like put something like a scalar to normalize it.
It won't help. It's not defined. And actually, philosophically, it has even a worse consequence, because orthogonality is not well defined. The eigenvectors are not well defined. They don't belong actually to the Hilbert space of the operator. But you can't get as a result of experimental position. So we hear it once and we ignore it from here on. In a moment, we'll see what it does to momentum. The point is that both momentum and position are unmeasurable. What do I mean unmeasurable? Not that you can't measure them, it's that a specific result you won't get a definite position. And that's not the result of the commutation relation of Poland. These eigenvectors get as a result as a result, a specific quantity. Okay, another point that creates a lot of confusion . Basically, what did we say about any wave function in Hilbert space? We can build it out of a basis that are the eigenvectors of some operator. So how do I build a wave function which is described in the base of position? Well, you can stop me a moment and say, sorry, we're doing it all the time. Psi of x, what does it mean? And we'll see in a moment what it really means. Okay, so if I want to write a wave function in the basis of x, if it would have been a discrete I would put here a sum over ai. Right? It's not discrete, it's a continuum. By definition. I want to know the amplitude of the wave function at point, I'm actually integrating over an infinite number of delta functions over the whole space in order to get the psi of x, which is the amplitude of the wave function. So nothing special about the position representation, except that it's a continuum. And when we're writing psi of x, it's the amplitude of the delta function at position x. Okay, I'm saying that it's hard to swallow, but the representation of the wave function in real space is the same as any other representation that we have. And that's the meaning of it. Writing down psi of x tells me I'm going over all the amplitudes, but getting one special position. Yeah.
Can you explain how you go from the second line to the third line?
Okay, here what happened is basically let me see if I can do it in a simpler way. We'll do it in 2 stages here. You know what? The easiest way would be actually writing down here. I want to know the amplitude at a given position, right? So okay. Because it's Dirac orthogonality between x and x0. Fine. What does it mean? That when I'm looking in the x representation on the wave function at point x0, just the scalar multiplication between the eigenvalue, eigenvector at point x and the wave function, right? So basically, psi of x is just the amplitude of the wave function multiplied by the eigenvector as everywhere else. But since we are working all the time in the same representation in x, simply psi of x. Nothing special except that we have these delta functions. Okay, let's see the mirror image. It will help us to understand, and that is the momentum space. Okay, that's a definition of the momentum operator. This is just the general way how we write down always any operator, any eigenvalue, an eigenvector equation for any operator. Okay, since I've written down my operator in the x basis, in space spaces, let's continue at the moment to use this representation. Okay, lovely. So this is the eigenvector of the momentum in the x basis. This is just rewriting the eigenvector and eigenvalue equation. That's a first order differential equation that you have met several times. Stick it in back here, performs a derivative, and you get what's written here. Now, physicists tend to be a very lazy lot and don't like to write h bar a lot of times. So they write the K operator, which is just this connection. K0 is H bar. That's the way around. So, K0 I've written correctly. And then, instead of writing all this stuff, you can simply write down the K operator if you want, but usually they just write down I K0 X, and if you want to translate it to momentum, just add the H bar with it. Okay. Well, if that's the eigen vector, let's check orthogonality.
Can I ask you something?
Sure. Let me finish here. Yes.
You said that we need to define a certain K operator for using that equation. Isn't it just the Breuer or something? So why do you need an operator for that?
Well, because I have an any physical, measurable physical quantity as an operator.
No, I know. I mean for K. Why you said that they're not.
I can define if I feel like.
Oh.
It's completely okay. I can measure momentum, or I can measure.
You can measure K.
K. Yeah.
Oh, you just divide by okay.
Same way.
But it's weird. You don't have units for K. So why?
Yes, you have.
No, because H bar takes all the units.
No, it's fine. So
Oh no, you have 1 over it. Never mind.
still have 1 over length for
Yeah,
as units
yeah,
for
yeah,
K.
Yeah.
You have to have it because all of this has to
That's the non-unit.
have no units.
units.
So if X has units of length, it has to be 1. Okay, so I'm going and performing scalar multiplication of P0 and P. Minus because it's on the left side, it's a complex. Good old friend, the delta function. Almost. Okay, but this I can correct easily. I had here no normalization. Called the Dirac normalization in order to get here 1. Again, this eigenvector is not in the Hilbert space. Why?
Because it doesn't have a definition.
It doesn't have a normalization. Try to normalize it, you'll get your infinity. It has only the Dirac normalization. Okay, another amusing fact that probably you can guess by now. Let's say I'm given a wave function psi x. What are the values of momentums that I can measure?
Eigenvalues on the operator.
Yes, but for this specific guy, what is the amplitude of measuring a specific value of P or K? Right? By definition. That is the amplitude of measuring some value of K. This guy? What do you call this integral?
Fourier transform.
Fourier transform. Therefore, if I want to know what is the amplitude corresponding to the basis of the eigenvalues of the momentum operator, just perform a Fourier transform. For our amusement, just a moment. What are the amplitudes in K-space of measuring a wave function that is localized at a specific point, which is an eigenvector of space at point x0?
It's a number.
Of course it's a number.
Constant.
dx e to the power minus I kx over 2 pi right? And as we know, integrals with delta functions are the easiest in the world. Right? What is the probability of measuring it at a given k? Probability is amplitude squared. My annoying normalization, but what it tells us Same probability for any momentum. Well, it's not surprising. We know to build a delta function you need equal contributions from all values of k. That's why both of these eigenvectors are not in my Hilbert space physically. In order to measure something at a definite point, it will have an infinite momentum. You have to throw in. It's like in when you did wave physics. How do you build a wave that is localized at one point only? You have to give components of all momentum, of all k's, right? Can't be done physically. Same way, if you want a pure value of momentum, it's all over your space. So what was the solution there in wave physics? Said that in reality, with what do you deal?
Uncertain.
There we didn't use certainty, it's classical. You always dealt with wave packets. Right? If you have a signal in frequency space, anyone here did something connected with? You never have a delta function in frequency. You can't produce a wave function that, an electromagnetic pulse or a wave that has a sharp frequency. Always has some width. You can't produce a signal that is smeared to infinity. Always has some boundary. Always exists. So it's always a wave packet. The same thing here. At the end of the day, when you play with transformation between questions about what is the momentum and what is the position of an electron, you're actually asking about a wave packet that has some finite range of momentum and a finite range of position. Okay, let's take a break here, and after I'll show another. This is extremely annoying because it's not normalizable in the usual sense. We'll see how we can deal with it so it will give us less of a mathematical problem. Okay, and that we'll do after the break till 3:25. Okay, so when we use Dirac normalizations, usually we get something that is somewhat inconvenient. It gets us stuck in understanding. We want to write the wave function of momentum. The basis of momentum, it's not normalizable. Problematic. Now for the position space, it's very natural how we correct it. How we correct it? Simply we discretize space. Let's say if you're going and solving Schrödinger equation on the computer, what do?
You define the boundaries.
Not only a boundary, I define a mesh. Let's say in one dimension, I just write down a constant distance between points and use it as a discrete positions. And then I can write down the usual linear algebra, just a finite number of points. What do I do in momentum space? Actually, it's a cute thing that has a lot of implications on solid state physics and on basically also field theory, because it gives us the possibility to talk about momentum which is discrete, which makes life much simpler. Okay, so how do I do it? So it's periodic boundary condition. Now, the easiest way to imagine it, think about a one-dimensional system. And if it's infinite, it's infinite. Okay, you need an infinite number of momenta, eigenvectors, or an infinite amount of position eigenvectors. But let's take the thing and think of it as a ring. Then you have a periodic boundary condition. Whatever left from here comes back here. What's nice about it? It's finite. Okay, let's try to understand what does it mean. Let's say I have a wave function in the X representation and I'm not worrying at the moment about normalization. Okay? Is that well defined on the ring? No, because if I go in X, I go once, twice, 3 times, I get a different value each time.
Why?
Because if I take here any value of kx, and I multiply it by 0, L, 2L, 4L, all of them falling on the same point, I could get different values of the amplitude. It's not well defined. So what is the boundary conditions that I have with periodic boundary conditions? I have to require right? Because if I move in my ring and go a distance of L, I return to the same point. It's the same point I should see is the same amplitude. So, when is this condition fulfilled?
When k equals to n pi.
Two pi or any multiplication of 2 pi? Okay. Can do it also for 2 dimension. Let's say a cylinder would have periodic boundary conditions in one direction, but not in the other direction. I connect it. I built a torus. I have it in 2 directions. Actually, I can require this boundary condition for any dimension. I just can't plot it, show it on the plan. So basically, periodic boundary condition in any dimension tells you that Ki times Li has to be 2 pi times Ni. X, Y, Z, W, V, whatever you want to name your d-dimensional space. Now, what does it mean? It basically means that the fact that I have this closure requires me to have discrete values of k. Otherwise, I can't write down a meaningful wave function for this system. And if you want to use high language, it tells you something about the topology of the system. It tells you whether you enclose something around the system and return to the same point. Like the questions that cosmologists ask themselves: is the universe open or closed? If it would have been one dimension, the question is, do you start in one direction, you continue forever? That's an open universe. If after some distance L you return to your same position, you're in a closed universe. Okay, and this makes life much easier for writing down the eigenvalues and eigenfunctions of the momentum. because generalization of what we have written here these are the possible eigenvalues of K in periodic boundary condition. Okay, we'll see in a moment. Yeah.
But it's discrete. That takes you to like finite K.
Once I claim that I have periodic boundary condition or my geometry is built in this way, I can look on it from two different directions. One is indeed my space is constructed in this way. I live on a ring. I live on a torus, I live on whatever you're calling it in 3 dimensions. Then, if it's true, you have discrete values of K.
So how can you do integer and not sum?
How can I do?
Integer instead of sum.
No, sum is fine. Integrals you don't have. You have summations. Your Dirac delta functions become usual chronicle delta functions. That's good, actually.
But you can do it on the space base. You have to use integral.
Yeah, my space. I didn't discretize space. Space is not discrete, but I have a periodic boundary condition. That's enough to change your the eigenvalues and the eigenvectors of the momentum space to something that is discrete. It's still infinite. N, X, and Y, and Z infinite. You still have an infinite number of them. But they're discrete, they're countable. Yeah.
So, how can you have from minus infinity to infinity? I mean, sign of minus, they would be linearly independent.
No, you let's go and remember.
Oh no, because of the I. Because of the I. No.
A concept that you're familiar since kindergarten, counting. You can count, and any numbers that you'll come to me and say it's the largest, I'll tell you add 1. It goes to infinite. It's a size of infinity. It's Aleph 0 if you want, but to whomever that means anything.
Oh.
Actually, how many of you heard that we are living in more than 4 dimensions, 3 space and 1 time? Only 2 of you? Nobody here reads popular science. Come on, the string theory tells you you have 10 or 11, depending what version. Did you ever stop and ask, look, I'm walking around for 20 plus years or perhaps a bit less around this world, and I have never seen anything beyond spatial dimensions. How can that be? So
We're three-dimensional creatures, so we are, how can I say, orthogonal, maybe, more dimensions.
no, much simpler than that.
Maybe I heard an explanation that you roll up some dimension and then you get new ones. Something like that.
The
Or you
roll
can see
up
it.
is very important. The rest, you don't get new ones.
So you don't see it maybe because you live on the roll up?
No, it's even without quantum mechanics, you can't understand why you don't see it. With quantum mechanics, you can completely understand it. And that's the answer. Let's say I go and solve my Schrödinger equation for this periodic boundary conditions. What are the energies, the eigenvalues of the energies?
Eigenvectors.
Eigenvalues,
This case.
h bar square k square over 2m, right? Let me write down explicitly. Well, h bar over 2m, h bar square over 2m, I'm pulling outside. These are the energies that I see. Now, for simplicity, I won't go into 10 dimensions. I'll go into 2 dimensions, 2 large dimensions, and 1 small dimension. Okay, so let's say Lx, Ly are large dimensions, and Lz is a small dimension. Okay? Now I'm starting to measure all the spectrum of energies that I can measure. Okay, I start from an X and Y and Z. Okay, that's the lowest. Anything else will have higher energy. What are the next highest energies?
Highest?
The next higher energies. This is a ground state. Either one. Let's assume that Lx is a bit larger than Lz. So this will be the next one. Right, and I can continue this list forward. Now, when will I change NZ? Because LZ is very small. If I put here a value of NZ that's not equal 0, I get a huge energy. Right?
That's after you went through all the ends on LX
I
and
went
L1.
over a lot of NX and NYs to a point where I must change NZ to get the next one. Meaning that if I'm a creature living in this system, and I'm measuring the spectrum of energies of free particles, and I don't have infinite energy. I'm not aware that there is an LZ in my game. Just because it's always zero, it's not in the game. If I'm looking what happens in collisions and stuff between particles, it's always a game between NX and NY. I don't see any influence of NZ because I don't have enough energy. So when they built the Large Hadron Collider, and perhaps some of you heard, perhaps they will be able to see higher dimensions. What does it mean? They hope that they'll have enough energy, perhaps, to move the next dimension value of n whatever. What will we call the fourth one? V, W, and V and W, whatever. So you'll see some difference in the experiment. They haven't seen anything, but that's the idea. And that's why they can tell you, well, we have only 3 dimensions, and all the other dimensions are curved up. Curved up, meaning it will cost a huge amount of energy to move from the values of 0 to higher ones. Yeah, someone.
That's why we see in 2 dimension, like because if you're getting higher and higher and higher, we can see the whole like.
No, that's why you can't say we are living in 3 dimensions, but there are 6 compactified, meaning a very small radius, additional dimensions. What does it mean?
But we see in 2 dimensions.
Seeing is already physiology, perhaps also psychology, but I'm not talking about seeing. Is going to and doing an experiment. All you see in all experiments that were done to this point could be explained as motion of particles in 3 dimensions. You don't need anything. Now, question. Is it because you didn't have enough energy, or because there aren't additional dimensions? Open question. People propagate string theory tell you, no, it's because you don't have enough energy. So perhaps go back to experiments at Probe as a Big Bang where we had a lot of energy. Perhaps in some other configuration you can. At the moment we don't have any evidence for other dimension. And it's not that we are living on, we are big, or it's just a question of seeing the energy. Because in quantum mechanics, short distances, large energy. That's why colliders, which want to check the behavior of physics on small scales, need a lot of energy. Okay, so we have our eigenvalues. How do we normalize it? Right? Okay, so I have a simple, nice, and well-defined eigenvector. Yeah,
Why didn't you use sinus instead of EIK?
because sinus makes no sense here.
Why? It's a periodic.
Because it's periodic, it doesn't make any sense. When do you use a sinus?
One dimension?
This is one dimension.
Standing the solution.
When I have two boundary points that I want to always hold at zero. A clamped wire. Right? Then you have 2 points 0 and L. And at point 0 and L,
They
have to be, the wave function has to be 0. If I'm taking a solution, let's demonstrate it simply on two, and it's important. Let's take it to infinity, these boundaries, and I have between 0 and L. Okay, if I have such a thing with a potential that you have done, I think, even in the last exercise. Right? So what are the solutions of this guy?
sinus.
Sinus. Right? Why are these the solution? I can explain it in two different ways. Now that we know the eigenfunctions of momentum. One, I want psi of 0 to be equal to pi of L, but to be equal 0. Right? Okay, that's a sign. Now, physics. What is this guy? You have to have your sign. That's the definition of science. What is the average momentum?
0.
0 must be, because I have the same probability of measuring k and minus k. Why is the momentum 0? Because it can't go anywhere. It's stuck in this well. Right? It doesn't go anywhere. On the other hand, if I'm on the ring, it can go around and around and around to its heart content forever. No problem. On the other hand, and what is the probability of finding it somewhere in this on this ring? The probability
On the ring is 1. stays in the
It stays on the ring, but in any position, P of X.
Oh.
1 over L. The same probability of finding it anywhere. But if you're telling me the solution here is sine, there are positions on the rings that you can't find it, right? Because there are nodes of sinus, and the probability there would be sinus square, and it's 0, right? Why on a ring that has no potential, nothing special on a particular point, is the probability of finding this particle 0? Makes no sense. So, indeed, on this geometry, you have sines. On this geometry, you don't have sines. You have e to the power ikx.
Because you don't have like the contribution from the minus ik.
Yeah, I can have. Here I can't have only a pure wave. Why can't I have it? Pure momentum. Because if I had pure momentum, I wouldn't be there. It would be somewhere else, but that's a well. Everywhere else costs me a huge amount of energy. Can't be there. On the other hand, here, no problem. Continue on going around and around as you wish, doesn't matter. So, both mathematically and physically, this type of systems, sinuses solve it. This type of system, e to the ik, it has also an additional physical consequence. Can I have, what is the ground state?
1 over L.
Here it's simple. Nx equals 0 is a kosher eigenvalue of the system of energy. Why? It's a case where my wave function is just 1 over square root of L. Fine, good. 0 momentum. If I'll choose here value k 0, I don't have that solution. Why is it? Because if I have to keep it 0 here and 0 here and not pay any energy to give it some maximum in between, it's nowhere. It's not there. So it's not a solution. Therefore here, the ground state starts as pi over L. I can't have here a constant solution because then it would be 0. It starts at 0 and ends at 0. Here, no problem. So these two systems behave physically totally different. Okay, if I now expand it for a three-dimensional solution, or d-dimensional solution, these are the eigenvectors of d-dimensional function. Well, normalized can work with everything there. Now, a lot of times in solid-state physics, you want to describe a piece of metal, but you don't care so much about what happens in the band. You do the calculation with periodic boundary condition, take L to infinity at the end, and if the result doesn't depend on L, all's well. Same for field theory. Next operator. Energy. Schrödinger equation. The Schrödinger equation is simply the eigenvalue and eigenvector equation of the energy operator. So, I get a set of eigenvectors, I get a set of eigenvalues, that is solving the Schrödinger equation, and you just created a basis in the energy basis. Nothing more, nothing less. Now, to our pet question during all this lecture. Is it continuous or is it discrete?
Discrete.
Discrete. Any other answers?
Depends on
Lovely. Depends. Depends on your system. Depends on age. We will go into it in more detail further on, but if you have a bound region of energy, of potential, it would be discrete. If you have a region of that the particle can move out of it, it will be continuous. So, if we'll ask the question, what is the spectrum of the hydrogen atom? Is it discrete or continuous? The answer would be, depends on energy. For energies below ionization energy, it's discrete. But the electron can leave completely the hydrogen atom and become essentially free. Then it will have a continuous spectrum. That's the ionization of an atom. The electron leaves the atom and lives happily, freely outside of it. Yeah.
But only in energy that are higher from the potential.
Exactly. But the potential is Coulomb potential. Coulomb potential at infinity goes to zero, not to an infinite value. So if you kick it above this threshold,
It can be at any energy.
it could be at any energy. You have continuum. Only if it's below and bounded to the atom, which is the other way to say that it can't leave it, then it's discrete. If I'll take this problem and instead of taking it to infinity, give a finite value, so you usually don't solve it in exercises in quantum mechanics for the simple reason that the mathematics is messy in this case, but the physics is very clear. You start by having levels that are discrete. They close to the edge, they become more and more dense, and here they are a continuum. So sewing together all these boundaries is mathematically not something we want to throw students to do, but the physics is very clear. This problem has discrete, becomes denser and denser, and then it's continuum. Same thing for the hydrogen atom, which this is a Coulomb potential. Here you have discrete energies. You come to here, they become more and more dense, and here they are a continuum. So basically, the energy basis has one huge advantage on other bases, and therefore you're all the day solving Schrödinger equations in quantum mechanics. Because then it's very easy to write the development in time. We did it in an exercise where we discussed it a bit, but now I'll re-emphasize it. Like with any other bases, I can write down the wave function for any given wave function. Okay, and that's not different than any other bases that I have. Could write it in case, could write it in position space, doesn't make any difference. Where it does make a huge difference in the calculation is if I want to write the time development. Because here becomes much easier. And that's the reason that any questions that I presented on time development, you usually try to move to energy basis. How do you move to energy basis? Same as I move to any other basis. Calculate scalar multiplication of the basis times the wave function, and you have the amplitudes. And since then, smooth sailing. But to do it, you have to find the eigenvalues and eigenvectors of the Schrödinger equation. So that's why half of the time you spend in quantum mechanics on solving the Schrödinger equation. What does it mean? Finding the eigenvalues and eigenvectors of the energy of the electron. Because if you stop and think about it a minute, usually people don't do it. When someone comes, let's say the hydrogen atoms, they are asking you, what is the wave function of an electron around the hydrogen atom? What is the answer?
Can you repeat the question?
What is the wave function of an electron around the hydrogen atom?
Depends on what basis.
No, it doesn't depend on the basis. The representation depends on the basis. The wave function doesn't.
Maybe at what
Depends
time.
on the energy that he's in. Like,
Who told you that it's in a specific energy? If someone comes and asks you what is the wave function of an electron around,
oh, it depends on the potential.
no, it depends on the initial conditions. I don't know. Sorry, I can't tell you. But if you give me the wave function at a given time, I know the solutions of the basis of energy for the hydrogen atom, and I can tell you how this wave function will develop with time. If you told me in the beginning I measured this electron at a given energy, I still can't tell you anything. Not sure you touched upon it. We will do it. The hydrogen atom has a lot of degeneracies in energy. So if I'm telling you an energy, it doesn't specify the wave function I'm talking about. So you have to measure energy, angular momentum, and the z component of the angular momentum in order for me to tell you what was the wave function. So when they're telling you solve the Schrödinger equation, usually they mean find the basis and find the spectrum, the possible eigenvalues. Don't want to start. We are moving from here to basically the trying to quantify the well-known description of Heisenberg on uncertainty. You have seen somewhere. Something like that. We will quantify it, calculate it, and see how we get it. And actually, it's one of a series. Delta T and delta E have also uncertainty relations, and others too. But what we'll do this thing and show from where this limit comes. Basically, we will show that any wave functions that we can come up with, the variance of x times the variance of p has to be larger than h bar over 2. But actually, at the moment, we can answer one of these questions. If I know for certainty the position, assuming I can do, what is the uncertainty in momentum?
Can't tell which k. It's all the k's.
Yeah,
Okay, it's infinite. The other way around,
And they have the same probability
to be in any one of them. So it's infinite uncertainty in P. If I know P exactly, I don't know the position. Now, the question is, can I be clever enough to build some wave function where this is minimal? And we will show that the best constructed wave functions that we can think about, you'll still have an uncertainty of which is equal or larger than h bar over 2. And actually this becomes very important in things like communication. You want to have a very precise frequency, but a very well-defined size of the pulse. And you have a combination which gives you the best possibility of minimizing the uncertainty in one and the other.
Gaussian.
Gaussian. That's this miracle function that it's the Fourier transform of one is also of a Gaussian is also a Gaussian. It's a decreasing frequency. Okay, so we'll stop here. Continuing next lecture. And people who had additional questions were invited.
אני חושבת שלא הבנתי משהו מהותי. מה הכוונה שאתה אומר על למדוד את K?
למדוד את התמה, תמה הוא גודל פיזיקלי.
שאתה מדבר על K, אתה מדבר על K.
אמרתי שאנחנו עצלנים ובמקום